Okay, let me begin just with the motivation. And I want to construct a uniform row algebra of a group, and this can be done in two different ways. So you have a finitely generated discrete group. You can look at the left regular representation of the group. So you have it here. And this provides you with a bunch of unitary operators. You can throw in diagonal operators, and you generate a C-star algebra out of it. Everything lives, as I said, in little L2 of G. There is a second way of looking at this uniform row algebra, which is in a sense more generic because it goes to uses a metric space. In the case of a group, you take the Cayley graph where the edges are labeled by the generators, K, and then you take the path length metric, and this gives you C-star algebra, which is generated by all operators with bounded propagation on this metric, on this graph. Of course, it turns out that these two algebras are the same. And so you have two different ways to look at them. And there are many connections between the large scale geometry of the group and C-star properties of this uniform row algebras of this class of C-star algebras. So the aim of this talk is just to replace the group by an inverse semigroup to study amenability versus paradoxical decompositions of this new object, new category, to determine a metric structure for the inverse semigroup in terms of a certain graph, and to do the similar construction we had for the case of groups and analyze large scale invariants of this new object, new metric space. Okay, so before I go to inverse semigroup, let me say why is it interesting? Well, one of the important things here is that in a semigroup, contrary to the group case, the dynamics is singular. And by which I mean that the action of a semigroup on itself is certainly non-injective. And when you move around sets by this dynamics, you can change very much the cardinality of the sets. I also prefer blackboard presentation. So here is my very professional picture. Semigroups may have a zero, and so you may very well shrink by multiplication a very big set into a single point. Okay, that's typical, the typical dynamical behavior of inverse semigroups, which we find interesting to address all these questions. So at the level of general semigroups, there is a notion of amenability due to Day, in the 57, he gave this definition, and it's very close to the usual one of von Neumann in the case of groups. So a semigroup is amenable if it has a finitely additive total probability measure, and here comes the important thing, which is invariant under pre-images. Okay, so here you have the invariance under the pre-images. Okay, this is of course a very, very strong definition, and Day itself, he noticed that there is a finite semigroup that is non-amenable, even two elements. Okay, and also in this, and due to this singular dynamics, all the classical equivalences between amenability, non-existence of paradoxical decompositions, existence of Foelner nets, etc., they do not hold anymore. So that makes the category interesting, at least from this point of view. There is a second notion that avoids, in a sense, the use of pre-images, which is called measurability. You say that the semigroup is measurable, meaning that you have a finitely additive total probability measure, which is now invariant under this push forward. Yeah, so you move your set A in the semigroup forward, so no pre-image. And but this is even a stronger notion that so implies amenability. So this is for general semigroups, and let me now move to inverse semigroups. Let me just remind the definition. An inverse a semigroup is inverse if any S has a unique S star satisfying these two conditions. And these kind of structure, or this class of semigroups has a lot of structure, which I'm not going to enter, but let me maybe mention the projections. You have in the inverse semigroup an abelian subsemigroup of all projections, which are of the form S star S. With these equations, you see that these are projections. And in fact, coming back to groups, you can think of a group as being an inverse semigroup with a single projection, namely the identity of the group. Okay? Never mind the other properties. The important thing about inverse semigroups is their dynamical behavior. So you can think of the following representation: the semigroup acting on itself and moving a certain domain onto a range, another subset. Here you have the definition of the domain. It's not so important for the moment. So the nice thing the picture you have to have in mind is that the action is still singular, but it's locally bijective. Okay, so this is a kind of representation by partial bijections. Okay, so you move the blue set here onto the red one by S, and you go back with S star. Okay, once you have this dynamical picture clear in mind, you can start with analyzing, saying what is a paradoxical decomposition, and you do it exactly as in the case of groups. You have the semigroup, you split it in A and B pieces, and once you move the A pieces, you can get the whole semigroup, and you can move the B pieces and get, again, the whole semigroup. The only difference is now that you take domains into account. To move A1 by S1, you have to make sure that A1 is in the right domain to be applied. Yeah, so in this picture again, so this partitioning of the semigroup has to be done in relation to the corresponding dynamics, and you place the subsets in the right place, in the right domain. So the first thing we did in this first article where we analyzed these notions was to take these notions of amenability, so the invariance and the pre-images. So this is a measure defining amenability. And then we split this condition into two conditions. One is purely dynamical, and we call it domain measurability because you push forward. But you push forward only the subsets that lie in the correct domain. Yeah, so this is a dynamical condition. And the second one is a localization condition that tells you that essentially the mass of A is concentrated on the corresponding domains. Yeah, I'm not going to mention this further, but Day's amenability splits into these two conditions, and we are going to focus on the first one, domain measurability. Yeah, and you see you have no pre-image here anymore. Okay. Let's go to the C-star algebra part. Inverse semigroups do have a very nice left regular representation. You see you have a kernel. It's not going to be unitary anymore, but you can represent the inverse semigroup by partial isometries. Once you have this bunch of partial isometries, you can throw in the diagonal operators described in terms of L infinity functions sitting on the diagonal, and then you generate the algebra RS, which generalizes the one we had before, RG. Okay, so the first result I want to mention is the following. Given a countable discrete inverse semigroup, the following four conditions are equivalent. So the first two refer to the semigroup itself. Yeah, so S is domain measurable, so this purely dynamical invariance condition on the measure, even only if it's not domain paradoxical, which was this paradoxical decomposition taking into account the domains. And these two properties, each of it, can be captured by C-star properties of the algebra RS we had before. And this is the case, so it's domain measurable if and only if the C-star algebra RS has an amenable trace or is not properly infinite, which is a way of capturing the non-paradoxicality of the algebra. Okay, I'm not going to say anything about the proof, but tell you that the domain measures, not the invariance and the pre-images, but domain measures correspond one-to-one to amenable traces of the C-star algebra. Okay, so that's one result. And let's move to the metric aspect Yeah, I told you I want to define a metric structure on S. So we want to write RS, or to prove this equality of RS as a uniform row algebra over a honest metric space with a certain metric. And let me just advance that the Cayley graph, contrary to the case of groups, will not do. For this, to explain this, or to give you an idea of why this is so, so consider the following matrix units. So everything lives now, the algebra RS, and the one I'm going to construct in a minute, lives, of course, in little L2 of S. My semigroup is discrete. And so you can consider this matrix unit sending delta Z, the canonical basis on L2 of S, into delta Y, provided Z is equal to X. And of course, whatever metric you may guess on S, if the distance between X and Y is less than infinity, then these guys, these matrix units are in the uniform row algebra because they have, by construction, bounded propagation. But if the domain projection of X, X star X, and the domain projection of Y, Y star Y are different, then these elements, these matrix units, are not going to be in RS. So you will have a strict containment in this equation here. Okay, this fact, yeah, forces to rediscover an old friend, which are the so-called green relations in a semigroup, which has given us as follow, left, because I'm multiplying from the left. So for any X, you define the L class, the left class, to be all those elements in the semigroup, such that the domain projection, so X star X, is equal to S star S. And the nice thing about these classes is that they just contain one projection. So you can use the projection to label the classes. Okay, so now we go for the graph and for the metric structure. You take the elements of this class, this is a finite, symmetric generating set generating the semigroup, and then you use this generating set to label the edges of the graph of the left class L of X star X. Okay, and then you use as a metric the path length in the graph. Yeah? So whenever you have 2 points in this class and you have a label, an element of the generator, it's important to note that if you can go from X to Y via one generator, you can turn back. So the graph here is undirected. And because of the reason I told you before, that you have to have infinite distance between different classes, you can split, so to say, the metric structure you are interested in as, and this is the graph lambda S, is a disjoint union of the left classes LE, and you put each class at infinite distance, provided that the projections, of course, are different. Maybe if you see Schützenberger graphs, which is the name of these graphs associated to the L classes, if you see it for the first time, maybe it's too fast and time is not flowing slower. Let me give you
just a very quick question. What in the last slide, what did you mean by symmetric in a generating set?
Symmetric, yeah, well, that if you have K in your generating set, then you have also K star. Okay. Yeah, it's symmetric means whenever, in the case of groups, if you have a generator K, you have K to the -1 also inside. Okay. It's a matter of symmetry, so that my graph is unoriented. So I have the K star also in the generating set.
Okay.
You see? Yeah. Okay. So maybe it's better to illustrate everything with an example. So take the bicyclic semigroup, which is generated by A and A star, with the only relation A star A is equal to 1. So I show you first the Cayley graph, which is this one here, also very professional. So you have 1A square, A to the power 3, and these are black edges in the sense that you can move up and down. Yeah, so you can go from A to 1, multiplying from the left with A star. But you can also go to the right by multiplying from the right with A star, but you cannot come back. So these red edges are oriented. Yeah, and you have the projections I mentioned before sitting here in the diagonal. So one is the biggest projection, then you have A star, and so on. Okay, and the way to produce the metric structure we are interested in, which is this joint collection of Schützenberger graphs, is just deleting the oriented edges. Okay, and it's clear that you cannot put distance 1 between 1 and A star, because otherwise you will not get the inclusion of C-star algebra. So you delete, you get a bunch of path graphs of infinite distance from each other, and that's the metric structure we are interested in. So this is the lambda P1 in this example. Okay, let's go for the first example. So imagine that you have a countable, not necessarily finitely generated inverse semigroup. Then you have this joint union of Schützenberger graphs. Then the two algebras I mentioned before are the same, provided S satisfies a certain finitary condition, which we call finite labability, and which I will explain in a minute, but which contains, for instance, the finitely generated inverse semigroups. Okay, so if S is finitely generated, then these two algebras are the same. If not, you have this condition, yeah, and which very briefly, the idea is the following. So you have again your inverse semigroup, you have your symmetric generating set, and it's finitely labelable if you can choose a finite number of labels, and you have a constant C bigger than 1 or equal than 1, such that each edge in the graph, which is joined by a generator, can be joined also by a collection of edges in this K1, in this finite K1. Probably it's going to be a longer path, but the length of the path is uniformly bounded above by this C. Yeah, and that's the idea of finite labability. Okay, let me just show you my last slide. So under certain technical conditions, finite labability is one of those. You have an inverse semigroup, countable discrete, and you have your metric structure. And the first thing, well, you can now start to address large-scale properties of this lambda S. And one of it is that domain measurability is a quasi-isometric invariant of S, okay? But not amenability in the sense of Tate. So this is one of the results. And the second one, of course, property A is a super important property. And it is, in a sense, a weakening of amenability in this coarse metric scenario. And you can also prove a result in this context for inverse semigroups that tells you that if this metric structure has property A uniformly over all classes, then this is the case if the algebra RS is nuclear or RS is an exact C-star algebra. Okay, so these are just two properties, two things that you can prove in this case. And what else? Well, maybe let me just concentrate on the second one, since I'm almost out of time. For us, at least, inverse semigroups provide really a huge class of examples to try to analyze or start analyzing large-scale properties of this new class. Yeah, it can be really a source of examples, providing you maybe new insight to construct maybe examples of semigroups not having property A, etc., etc. I also prepared a slide. Well, it was there yesterday with references. Maybe I can send Sarah the slides again in case you want to share it. And there is 18, 19 references in case you like these kind of analysis. Okay, thank you very much.